our next topic, and this one goes for about 4 weeks, and there will be a handout. I started doing it last night, but then I got really distracted with this really cool website. Okay, so linear functions. This is syllabus outcomes 6.1 to 6.5 and 6.7. I've already posted those syllabus outcomes on Moodle for you. I've crossed out 6.6 and 6.8 because they are not 2-unit maths or mathematics outcomes. They are the enriched extension outcomes. So you don't need to do those. Only 6.1 to 5 and 6.7. And Cartesian geometry isn't pointless. I found a not so appropriate version of that same phrase on a t-shirt that I shouldn't have shown you. I just thought I'd show you this. Here we go. The sound doesn't matter. Yes, this is the cheese roll.
Oh, the Switzerland.
No, England actually. They might do it in Switzerland too, and that might even be more dangerous.
Can we try this?
No, we're not trying a maths experiment doing cheese rolling. But why am I showing you this? Because it's funny, yes, true. For going down a slope. Now, when you looked at it front on, it didn't look that steep, does it? Like, that doesn't look that steep, but when you looked at it from the top then, it's pretty steep. And if, in case you're wondering, do they hurt themselves? Yes. What do they get? I'm not entirely sure. They win the cheese. Well, there you go. I think it might be easier to just go and buy some cheese rather than kill yourself rolling down that slope. Because it's incredibly steep. You look at that. It'd want to be expensive cheese. So, oh yeah, there's more of people doing whatever they can do to help themselves. You kind of hope the ground was really. I don't think he can say he actually ran down the hill so much as just bounced.
He made it to the bottom.
He did make it to the bottom. Good point.
I think he beat the cheese. Oh, no, he beat it.
This is a really good incline plane question. Okay, so that's an example of how steep the whole hill is. Now, that is a pretty steep hill. I don't quite know how grass grows on that hill, but anyway. So this brings us the concept of gradients. So this is a sign. You don't see many of these signs in Australia, but what does it mean? 10% gradient. What do you mean by gradient? What do you mean by 10% gradient?
The incline. 1/10 gradient.
Well, sorry, what was that, Rona?
Is that for every 100 metres goes that way, it goes 10 up?
For every 100 metres it goes 10 up. Why would it be 100 metres and 10 metres?
10%.
10 and 1, yeah. That's exactly what it means. So for every 100 metres it goes which way? So is it the diagonal? The sign itself's a little bit misleading.
Horizontal.
So yeah, so it's for every 100 metres it goes horizontally, it goes 10 up. That means it has a gradient of 10%. So that sign, as a mathematical thing, is not right. Why is it not right? What's the misinterpretation it gives you? Yeah, the misinterpretation is that the 100 metres is along the hypotenuse of the triangle, and that's not even the hypotenuse of the triangle. So, what sort of triangle should they have drawn to be more mathematically correct? A right-angled triangle. Why didn't they, do you reckon?
Because it's a triangular sign.
Because it fits nicer on the sign that way around. Okay? So define gradient for me. What does gradient mean? The slope of something. So what do we mean by slope?
The rise of the incline divided by the length of the incline.
Yeah, good old gradient equals rise over run, yeah. But I guess what I really want you to always remember, and it's very important that when we're doing maths that we don't get into the habit of just thinking in terms of formula. Okay, yes, it is the rise over the run, but think about it, what it actually means. And of course it is rise over run, where the run is how far horizontally you've gone, and the rise is how far vertically you've gone. So if you always remember back, gradient is how much you go up over how much you've gone across at right angles. It's not a new concept, but you've got to think in terms, not just in terms of the formula and m in linear equations and that sort of thing, because gradient is going to become more and more important to us the further we go down this course. Everyone's seen that before, haven't they? Yeah, cool. Okay. So tell me about the first one, the one over in the sort of top right-hand corner.
Negative 50%.
It's what, sorry?
Negative 50%.
Negative 50%. Well, let's not put a number to it because it's a bit hard to tell because there's no scales on there. But it's negative gradient, you reckon. How do you know it's negative?
Slopes down to the right.
It slopes down to the right. What's a good way of remembering that?
Down
The number
negative.
plane.
Down the number plane. There's no number planes there. Which way do we read? We read from left to right, yeah? So if I'm reading from left to right, so if I'm walking from left to right, and I hit that top left-hand corner one, what way do I go down? I go down it, don't I? So if I'm walking along, I'll go down that particular one. So therefore, the next one over in the top right-hand corner is positive, because as I'm walking from left to right, I go up. All right. What about the bottom left-hand one, the vertical line? What's the gradient of that? You've got a 1 in 2 chance of getting this right. 100% or 0? Which one is it? What was gradient? How did we define gradient? Rise over run. So when it's a vertical line, what's the run? 0. So anything divided by 0 is
A mathematical error.
a mathematical error. That's correct. Undefined is another way of writing it and quicker. Okay, so a vertical line has an undefined gradient, which therefore means the horizontal line, 0 gradient, because it's not going up for any that's going across. Okay, so always remember, rise over run. The run for this vertical line is 0, therefore the gradient is undefined because you cannot divide by 0. Is everyone cool with that? Yeah, everyone remembers that? So it's a negative gradient, positive gradient, 0 gradient, and an... Ooh, I got those around the wrong way. So the 0 gradient should say undefined and the undefined should say 0. Okay, finding the gradient of a straight line. So now we've just drawn on these axes. Previously all I had was a straight line. Is it any different, really? No.
Your axes aren't quite scale.
Said my axes aren't quite what?
To scale, not like symmetry. It's low, not as steep as it should be.
It's just saying the point of the first dot is actually 0.1.
Yes.
It does.
Doesn't
It's
make any
like
difference.
symmetry that's-
There's no symmetry. No, she's right. It doesn't make any difference. So all we do when we put axes on things, all we're doing is giving ourselves points of reference. So all the maths you've done previously, where you had to draw the axes and they had to be in red pen, they had to have arrows on them, you had to have them exactly the scale, all that sort of stuff, is kind of irrelevant. All we're doing is putting the axes somewhere, so we've got a point of reference. And when you do more physics later, you'll realise that becomes, you put your frame of reference where you want it to be. It's not defined, it's where you want it to be and everything else relates to that. So we choose 2 points, we draw a line between them. And we can only have one line between 2 points. To define a line, we must have 2 points. And for the sake of being general, we call the points x1, y1 and x2, y2. To find the gradient, we actually basically construct a right-angled triangle. And we construct a right-angled triangle because we want to have the rise over the run. So to find the rise, what we need to do is we need to find the height that it's gone up. So if we look there, the point x1, y1 obviously has a y coordinate y1, and the point x2, y2 obviously has a y coordinate y2. And we can find the difference between them is that rise. So the rise, as we've gone from y1 to y2, is given by y2 take away y1. And we can do exactly the same thing for the run. Obviously we've got the point x2 and the point x1. The difference as we've travelled from x1 to x2 is given by x2 minus x1. So we've now come up with expressions for the rise and the run in terms of any 2 particular points. Have you guys seen that derived that way before?
Yeah.
Yeah, good. So we know the gradient is rise over run, and the rise in this case is y2 minus y1, and the run is x2 minus x1. And we've come up with our formula for the gradient, was that?
Why is gradient M?
Why is gradient m? I don't know.
The G was taken by something else.
Yeah, gravity. I don't know. Find out. Yeah, it's one of those stupid things, yes. Okay, so the formula for gradient, everyone's seen that. Now, I would actually expect you to be able to derive that for me. It's not very hard. Okay, which brings us to tan. What am I, it is weird, it's capital theta. What am I talking about? Tan theta. If we call the angle in there theta, what can you tell me about tan theta? It's opposite over adjacent, that's correct. So the opposite is, what have we called it on here? The rise, and the adjacent is the, right, so tan of theta is the rise over the run, which is also the gradient. Okay, so that's that angle, which is also the angle down there. Why is it the angle down there as well? How could you show to me that that angle in the triangle is the same as the angle the line makes with the x-axis?
Corresponding angles in parallel lines.
Corresponding angles in parallel lines. Good answer. The two parallel lines being the run and the x-axis. Good. So from that we can see that tan of the angle the line makes with the x-axis is equal to the gradient. Now you need to be very careful with that, because if you get a negative, you've got to make sure your answer is going to be between what? No, it can actually be between 0 and 180 degrees. What you'll find is when we do trig and we do trig on the unit circle, which is taking trigonometry outside triangles, that all the trig ratios have different values for between 0 and 90, 90 and 180, 180 and 270, and 270 and 360. But for now, use your calculator. If I ask you to find the angle of something that makes with a positive x-axis, and that's generally the way it's asked, just use your calculator. If it gives you an angle that's between 0 and 180, you're fine. So with negative numbers, it will give you an angle between 0 and 180. We'll cover that more when we get to trigonometry. Is everyone happy with the fact that tan of the angle that makes with the axis is the gradient? Have you seen that before? No. Okay. Some of you may have, yeah. But it makes sense, doesn't it? Cool. All right, so a typical type of question is find the gradient of the line joining 2, 3 and 4, 7 and the angle that line makes with the x-axis. So all we do is we call the first point x1, y1 and the second point x2, y2, substitute straight in the formula to get a gradient of 2. Everyone's done that before. To find the tan, oops, all we do is use our calculator. Using the inverse tan function, and we get an angle. Always make sure that your angle's probably going to be realistic. Right, so if it's going from 2, 3 to 4, 7, it's going to be a positive, and it's a positive gradient. An angle of about 60 degrees would be about right if you drew a picture of it. The only other things we need to talk about today are parallel lines. And we've always talked about the fact that parallel lines have the same gradient. And this is why. If we have two parallel lines, then they must make angles of equal magnitude with the positive direction of the x-axis. And if they make angles of equal magnitude, therefore the gradients are the same.
So to do it the other way around, to go from the angle to the line, you just do norm tan rather than tan theta? Or
Yes,
tan
yes, yeah. Yeah. So if you're given the angle and you're asked to find the gradient, you do normal tan, yeah. So tan of the angle will give you the gradient, yeah. Which could be handy because you might know the angle at which it hits something or something like that. Yeah. So that's why parallel lines have the same gradient. And you need to remember that. The other thing you need to remember, and that's a sufficient proof, In the definition of the gradient, you can actually see that the angles are the same. And so the only other thing you need to know, if we've talked about parallel lines, will be they're not parallel there. Well, actually, it's not quite true. If they're not parallel, they're not necessarily perpendicular. But the other one we want is perpendicular lines. Okay, I'll come back to that if you need it. And the one thing you need to know with perpendicular lines is that the product of the gradient of two perpendicular lines is -1. Alright. So if we have a gradient of one line being M1 and the other line being M2, then if they are perpendicular, when you multiply the two gradients, you get -1. We will prove this when we do trigonometry on the unit circle, but we can't until we've done that. Alright. Everyone's seen that before too, haven't you? Yeah. I think that was it. Yeah. So parallel lines, same gradient. Perpendicular lines, the product of the gradients is -1. And the only other thing that's really important is that the gradient of a line is also equal to tan theta. That's the three things you've done that are possibly new for some of you today.
Can you show an example of a perpendicular line?
Show an example of a perpendicular line. What do you mean by show an example?
And how M2 and M1 product is -1.
I can do that. Alright, so say for example you've got, if we were asked to show, now we haven't covered the general form of the line, and y equals so you're asked to show that two lines are perpendicular. The first thing we need to do is we need to remember the general form of the equation of a straight line, which is what?
Mx plus c.
B in New South Wales, same thing, but we call it B up here. Yeah, I'm used to C as well. So we know the general form of a straight line is, it makes a huge difference.
Yeah. Because c is constant as well.
I agree with you. So the general form of the equation of a straight line is y equals mx plus b, where m is the gradient, of course, and b is the y-intercept. So from this one we can say that m1 is 2, m2 is -1/2. So we want to show that those two lines are perpendicular, and then we just say
So are you recording what you've written on the board?
Yep.
So this will all be there?
Yep. I hope so. So M1, M2, all you do is you substitute in 2 times -1/2, which equals -1. Therefore,
You should do it from the next one.
M1 is perpendicular to M2.
Sir, this
Yes.
is amazing when you write on the board, it appears on the laptop.
Huh?
When you write on the board, it appears on the laptop.
Of course it does.
Can we
You
just
just
do
do it from the next
as
room,
you
it'd be like
write?
totally awesome and creepy. It'd just be like random words appearing on the board.
Yeah, you can sit in the next room and what on the laptop and appear on the board.
No, you can't because we plug in.
Get it on cord.
Good idea. Get along with it.
There was a hole in the wall.
We could crank someone like that, though, couldn't we?
Yeah.
So that, if you're asked to show that two things are perpendicular, all you need to do is show that the product of their two gradients is -1.